Okay guys, so welcome back. This is integration by parts. It's the 11th video in the series, and it has to do with the product of functions. Let's take a look at the theorem for integration by parts. So it says, if u and v are functions of x and have continuous derivatives, then the following is true. The antiderivative of u dv is equal to u times v minus the antiderivative of v du. Now, I find that students always have a difficult time with this type of notation. So what we're going to do instead is we're going to take a look at my explanation and the formula that I like to use for integration by parts. So the first thing is to understand what integration by parts is. It is used when there's a product of functions that does not fit any of the previous patterns that we've seen. So in past videos, I've showed you different patterns that we have to recognize. Well, if it doesn't fit one of those patterns, then we should be using integration by parts. At the end of this video, I'm actually going to do a little summary of those patterns that we should be able to recognize, but we'll see that later on. And the other thing that we should know is that the inverse of the product rule is integration by parts. Not really that important, but you should know this. All right, pause the video. This is the formula we're going to be using. It looks a little bit complicated, but it actually isn't, and you'll understand why in a couple of minutes. So, the first thing we have to realize is that there's a product of functions. And what we're going to do is that we are going to assign which one of those functions is going to be f of x and which one is going to be the derivative of g of x. And then once we identify which is f of x and which is the derivative of f of x, of g of x, then all we need to do is find the derivative of f of x and the antiderivative of g prime of x. So let's take a look at the process. So as you can see, there's a product of two functions. Now technically, it would be a lot easier to simply multiply 2x times x plus 1. So we would end up with 2x squared plus 2x, and then simply anti-differentiate. However, we're going to use the process of integration by parts. So I'm going to show you two ways of doing this, or two options that we have. There's a more complicated option and a much easier option. Now, there's no wrong way of doing this. It's just that you try to find the easiest way of performing integration by parts depending on what you let f of x be and what you let g prime of x be. So, for the first option, what I decided was to make f of x 2x and the derivative of g of x, x plus 1. Now, once again, I chose those values. I could have done it the other way, and you'll see with the second option, I did choose the other way around, where I let f of x equal to x plus 1 and g prime of x equal to x. So, here we go. The first thing is simply identifying which is going to be f of x and which is going to be the derivative of g of x. Now, we simply find the derivative of f of x, in this case it's 2, and we find the antiderivative of x plus 1, so that we can obtain g of x, which is x squared over 2 plus x. Okay. Next, we have our formula. So it simply becomes a plug and play. 2x times x squared over 2 plus x minus the integral of 2 times x squared over 2 plus x. Okay. Now, we simply multiply the first part and find the antiderivative of the second part. Simplify, combine similar terms, and there's my antiderivative. This is called integration by parts. So, let's take a look at a second option. Let's say, for example, a student did something different, and they let f of x equal to x plus 1 and the derivative of g of x equal to 2x. Now, you take the derivative of f of x, you get 1, and the antiderivative of 2x, you end up with x squared. Once again, here's my formula. It becomes a plug and play. Product minus the integral of x squared. This one seems to be a little bit easier than the first one. Find my antiderivative, combine similar terms, and I end up with the exact same answer. So as you can see, the second option of letting f of x equal to x plus 1 and the derivative of g of x equal to 2x is a little bit easier than the first option. But once again, as you can see, it doesn't matter. So our goal is to try to find the easiest way of doing this. So let's take a look at the second example, and what you'll notice is that many times when it's a product with an exponential function with base e, most of the time we're going to have to use integration by parts. So we're going to let f of x equal to x and g prime of x equal to e to the x. Okay. Find the derivative of x, which is 1, and the antiderivative of e to the x, which is simply e to the x. Here's my formula. Replace the values. Find the antiderivative of e to the x, which is simply e to the x, and then don't forget to add your plus c as your constant. Third example, similar to the first one, or the second one I should say. So we're going to let f of x equal to 4x. We're going to let the derivative of g of x equal to e to the negative x. We find the derivative of f of x, which is 4. We find the antiderivative of e to the negative x, which ends up being negative e to the negative x. Okay, once again, here's my formula. Plug in the right values. Find the antiderivative of e to the negative x. Combine and add my c for my constant. So as you can see, integration by parts is really easy when you follow that formula that I gave you. All we have to do is identify our f of x and our g prime of x, and then find the derivative and antiderivative. And then we use the formula, replace the values, find the antiderivative again, and of course add my c for my constant. So let's take a look at the fourth example. We have a product of functions, x to the power of 4 times ln x. It doesn't seem to fit any of the previous patterns that we've seen, so therefore we're going to perform integration by parts. Okay, so I'm going to try this out and see what happens. I'm going to let f of x equal to x to the fourth, and I'll let the derivative of g of x equal to ln x. Find the derivative of f of x, I get 4x cubed, and the antiderivative of ln x is x ln x minus x. Now, this looks a little bit complicated. So you know what? Maybe I didn't make a right choice. Let me try the other way around and see what happens. So now I'm going to let f of x equal to ln x, the derivative equal to x to the fourth. Find the derivative of f of x, get 1 over x, and the antiderivative of x to the fourth is x to the fifth over 5. Okay, this seems to be a little bit easier to work with. Write down my formula. Put down the proper information, simplify the antiderivative right now, and I simply have the antiderivative of x to the fourth, which is quite easy to do. And there we go. Antiderivative. Okay, so we're going to take a look at a challenging problem. I consider this to be a more difficult problem. So the first thing I'm going to do is I'm going to rewrite this, and I'm going to rewrite this as a product. But what I want you to notice is that I actually only factored out x squared e to the x squared, and I left the x on top as the numerator of x squared plus 1 all squared. Now the reason why I'm doing that is because when I find the antiderivative, it's going to follow one of those patterns that we've seen in past videos, which is the integration of composite functions. So I'm going to let f of x equal to x squared e to the x squared, and the derivative of g of x equal to x times x squared plus 1 all to the negative 2. Alright, when I find the derivative of f of x, I end up with 2x e x squared times x squared plus 1. And when I find the antiderivative of x times x squared plus 1 to the negative 2, I end up with negative 1 over 2 times x squared plus 1. Okay, so far so good. So I have the derivative, and I have my antiderivative, I have my g of x, I have my f of x, so we're good to go. Here's my formula. Write in my values. Multiply, simplify what's in the integral, and now find the antiderivative. I end up with e to the x squared over 2. Common denominator, distribute and simplify, and there is my antiderivative. So as you can see, sometimes we have to break up the function in a particular way to help me find antiderivatives, or sometimes even derivatives. So once again, I would not have expected you to think of this. That's why I chose this example to show you. All right. Okay, so I think this is the best time to recap what we've seen in previous videos regarding recognizing specific patterns. So we have the first one, which is known as the integration of composite functions. We have the second one that is known as the general power rule of integration. We have the next one, which is logarithmic integration, exponential integration, bases other than e integration, and finally, of course, the integration by parts. Now remember, in the integration by parts, the part that has the antiderivative can have one of those patterns that we've previously seen. So this is a nice little recap of what we've seen in the last few videos, and I would definitely pause the video, write these down again so you have a collection of all of them, and there we go. And always, last but not least, practice, practice, practice. You need to practice this concept of integration by parts. It is excellent for the product of functions, and I hope you understood and I hope you enjoyed.